gaining. So now in that half cell, so these are not going to happen in one cell. There were two cells in the galvanic cell. So there's this half cell where is the anode, then there's this half cell where is the cathode. So you expect one process taking place here, the other process taking place there, because here there is losing of electrons, here there is gaining of electrons at the cathode. So whoever is gaining those electrons is supposed to be here, and whoever is losing those electrons is supposed to be here, and divided by the salt bridge. So what is happening at this particular cell is what is called a half reaction. And there is also another process that is happening here, another reaction called half reaction. So let's see what is happening in these two half reactions. So like we had established, ion in the equation is moving from ion 3 plus to ion 2 plus. And this is its half reaction. So the half reaction is specifically focusing on one particular substance. In this particular case, ion. So to move from ion 3 plus to ion 2 plus is gaining one electron, and the addition of one electron is known as reduction. So when this process happens, this is the potential that is generated, 0.77 volts. Okay? On the other hand, copper is gaining 2 electrons. Now, hold on here. I'll explain what is happening in this equation. We can see that copper moved from copper neutral to copper 2. So it was losing. But in the half reactions, or what you are going to be given in the exam or in the textbook, all half reactions are given as reduction. They are gaining electrons. So this is copper 2 to copper neutral. So it's gaining 2 electrons. And this is the potential that is generated when this happens. But in this particular case, copper was actually losing electrons to ion. So this is the correct equation. So this is a standard, and 0.34 volts is generated. But in our case, copper was actually losing electrons. So you change the sign of the standard electrode potential to negative. So you put negative on both sides, because what was happening? In another case, you find that copper will be gaining. So you have to follow this reduction equation. But for this particular case, it is the one that is losing. So you flip the signs, you give it negative. Okay. So now this also takes you back to something that you did probably in grade 1 or something, where you were being told that there's the reactivity series of metals. One is more reactive than the other, and so on and so forth. So you find that it follows that when two metals meet in this particular redox reaction, one will be gaining electrons from the other, then the other one will be losing electrons to the other. So the one that is more reactive mostly gains electrons from the other guy who will lose electrons to this more reactive. But that's another discussion for another day, because it's not consistent throughout. There are some other cases that need to be explained. But for now, at least you can get a glimpse of what is happening here. So meaning, should copper come in contact with a metal that is less reactive, it will be the one gaining electrons, and then you're going to follow this. But in this case, it is losing. So this equation will be given in the exam or in the textbook. So the moment you notice that in the equation, copper was actually doing the opposite, was losing, but what you have been given is gaining. So you flip this equation, you flip the sign from positive to negative. Okay. Now, each copper atom produces 2 electrons, as you can see in this as in the case here, because it was moved from copper to copper 2 plus. So meaning it was losing 2 electrons. Okay, so each copper atom produces 2 electrons, but each ion accepts only 1 electron. So as you can see from this half equation of ion was only gaining 1 electron. So it was moving from ion 3 to ion 2, only gaining 1 electron. So now, if copper is losing 2 electrons, where is the other electron going? So we need another ion to gain that other electron. That's why we are multiplying this half reaction throughout by 2. The basic principle here is to balance these electrons. So if copper is giving 2 electrons, then we need to multiply throughout the half reaction of ion by 2, so that we have 2 ions that are gaining, each one is gaining 1 electron to get to ion 2 plus. Now remember what we said, the integer that we use when balancing this equation doesn't affect the standard electrode potential. So it remains the same. We have not multiplied this by 2. I'm sure you remember this. All right. So basically, this is what is happening here. So this is the half reaction, and for reduction, this is half reaction for oxidation. So these are happening at the same time, and that's why it is called a redox reaction. Okay, and we quickly have to balance the electrons. So meaning this half reaction, we're going to multiply it. We just don't multiply the electrons, okay? Because it is this which is gaining electrons. So if you want to balance electrons, you multiply throughout by 2, so that the electrons that are being produced by copper atom to become copper ion, producing 2. These are the electrons that are going to be gained by the substance that is undergoing reduction, also to balance the electrons. So electrons here are critical when it comes to balancing. You can later on check that even the substances, iron and copper, they are also balanced. But what is important is the balancing of electrons. Okay, and you find that even in the main equation, eventually, the main equation, everything is going to balance out. But remember, when you multiply, we leave out the standard electrode potential. It is not affected by this integer that you have used to balance. And make sure that it's an integer, not a fraction. So overall balanced cell reaction. So we said we multiply throughout by 2, this half reaction. The potential remains the same. Then this one has been flipped, because in the actual reaction, in the actual redox reaction, it was actually copper losing electrons, becoming. So this is a standard, but in this equation, the standard has been altered. It is the opposite. Here it was gaining, that's why it has a positive value. Here it was losing to ion, so we have changed the sign to become negative. So a balanced cell reaction, therefore, will be that this copper plus 2 ion 3 plus will give copper 2 plus 2 ion 2 plus. Okay, therefore, the cell potential E naught of the cell, the entire cell. So we know that this cell, the galvanic cell, has got 2 compartments. There's the anode side and there's the cathode side. So when you add those 2 of the entire cell, we are basically have the E naught, the standard electrode potential of the cathode, minus the standard electrode potential of the anode. Okay, so what is happening here is that the E cell, therefore, the cathode is here 0.77 minus 0.77 0.34, which is the anode, and it gives you this value 0.43 volts. Okay, let me just check here.
Sir, I have a question.
Yes, go ahead.
On the anode there, it's negative 0.34. Are we not supposed to go with a negative?
No. So we're looking at the value. Look at let me go back to my slide. So I can see a hand from Mike Gura. After I finish talking, you can go ahead, Mike Gura. Let me just explain what somebody has asked here. Okay, I'm trying to get to. Yeah, so you've seen here. Are you able to see my mouse?
Yes, sir.
Where I'm pointing this equation here. So the original is in the reduction form, like I explained. So we have positive value. But in the equation, we change the sign. We are changing both sides, the E naught and this side, okay? So you can cancel out these negatives. You get a positive value. Then you subtract. What is important here is the value, okay? Is the value. So you have your answer there. You are not generating negative energy or negative electricity. I hope you get the concept.
Sir. I just wanted to add on, OVCL is taken as the cathode reaction minus the anode reaction. And basically at the cathode, we have reduction that takes place, and at the anode, we have oxidation that takes place. So when you make the when you make the reaction taking place at the anode negative, there's no need to make it negative again in the formula, because you have already made it negative by swapping the sign. So there's no need to make it negative again. Therefore, once you make it negative, just substitute it in your equation.
That's very good. That's very good. Please repeat for the sake of those that were dozing. Say it again. I can see them. They have switched off their cameras, but I know they are dozing. So just repeat and emphasize that.
So I was saying that the standard electrode potential equation is given as the electrode potential of the cathode minus the electrode potential of the anode. And at the cathode, we have reduction that takes place. And at the anode, we have oxidation that takes place. So for the 0.34, we have already made it negative by swapping the sign, because at the anode, that is where the loss of electron takes place. It is already negative, and therefore, when we substitute it in this equation, there is no need for us to make it negative again. But if you are using this equation, you will just need to put it as it is. So for example, you will say 0.77 minus 0.34, because you are just substituting it in this equation.
Thank you very much. That's great. That's great. Okay, so we like I said, we've flipped. Initially, it is supposed to be a reduction. So we've flipped it because we want to show that in the equation it was undergoing oxidation, and instead of the given value, which is reduction, So the sign was telling you that we've flipped this equation. So there's no need to do that again. Just pick this value and put it here. Then you do your subtraction, then you get your answer. Okay, so who is another one who was raising the hand? Go ahead. Or maybe you had the same question, so we can proceed. All right. Okay, so let's look at the line notation. Okay, I know you have another class at 11, so I need to give you time to go and join the other side. So the line notation used to describe electrochemical cell. So remember, the cell has two components. There are two half reactions. We have the side from the cathode, the side from the anode. Then, so this line notation will basically guide what is happening on which side of the cell. Okay. So since you are not going to be redrawing the galvanic cell all the time, but you can come up with some sort of representation, chemical representation of what is happening in the galvanic cell, because you are a chemist, you are not an artist. You don't need to start drawing everything that they are given there. You just need a representation in chemical sense. Then anode components are listed on the left. Please take note of that. Then cathode components are listed on the right, just like the way the galvanic cell was presented. So these are separated by double vertical lines, which indicate a salt bridge or porous disk. Okay, so what I'm saying is here, written here at the bottom. Okay, the concentration of aqueous solution should be specified in the notation when known. So once you know the concentration, remember it is one of the conditions that I had given, apart from the atmospheric pressure and the temperature. You also have the concentration that need to be specified, because in the future you will find that it's going to be used to determine a lot of factors about the processes that are happening in your battery or in your cell. Okay, so the concentration of the aqueous solution should be specified in the notation when known. So this is just an example. Okay, we have magnesium solid being transformed to magnesium 2+ in aqueous solution. Okay, so you can see that this process here is oxidation, because magnesium is losing electrons. So magnesium undergoes oxidation. Okay, then we have, so this will be shown at the anode, because at the anode that's where oxidation takes place. So this is the half reaction or the half equation. So magnesium arrow, magnesium 2+ plus 2 electrons. Okay, yeah. So this moves from solid to aqueous status. So if the concentration was known, it also has to be included. Now this is separated by the two vertical lines to indicate that there is a salt bridge here, and the salt bridge is a controller, so that there is no unnecessary mix-up of the solutions that are in both compartments, the anode and the cathode. Then the other half reaction that we are able to see on the right side, okay? So that's the cathode component, which are listed on the right side, where reduction takes place. So in this particular case, the half reaction, aluminium 3+ is gaining 3 electrons to become aluminium neutral. Okay, so this is what is happening at the cathode, or at the right side of this line notation. So sometimes you may be given a diagram where you have a galvanic cell, they'll show all the processes. Then you'll be required to come up with this line notation. Okay, so don't get mixed up. You can see clearly here that magnesium is moving from magnesium solid to aqueous. It's losing electrons, and this is oxidation, and this oxidation is happening at the anode. On the other side, on the right side of this line notation or representation of the galvanic cell, aluminium is gaining electron and is undergoing reduction, moving from aluminium 3+ to aluminium neutral, and this is happening at the cathode. So again, sometimes you may be given this line notation so that you get back to the galvanic cell, or you come up with these half reactions. So there's oxidation, there's reduction, and when these two are happening at the same time, collectively they are called a redox reaction. Each one will have its own compartment, and electrons will be flowing from one end to the other. They're going up there, passing through that wire we saw in the galvanic cell, and that flow of electrons will now generate current, which should now be used by your gadgets, either your phone, your watch, your vehicle, or anything else. So those are the cables you see connected to those batteries, so that they run whatever it is, whether it's your remote, your car, or anything else, from this chemical reaction. So now these are some of the issues that you as chemists, or especially those of us that are remaining with us in chemistry, you begin to look, is there a substance that we can find that can do a better job in terms of generating electricity, or that can last long in this particular substance? So this is what usually scientists have been focusing on, to find a combination that can give a long-lasting battery or a long-lasting cell, or that the one that can generate more potential, so that it can do more work as compared to what has been there in the past. And it's unfortunate your generation didn't witness those batteries. Others used to have black stuff inside there. Others used to have something that looked like porridge. So those were innovations that were being made from one point to the other to find a suitable material that eventually give a desired quality of a battery in terms of usage period, and also if possible, if it can be recharged, because most of these cells are just disposed once they are used, but can need to be recharged. So even the processes of recharging, especially in the case of a car battery, these are some of the things that we're going to explore. What happens during that process? What causes it to run out of the potential, and how do you do to regain that potential? Now, our interest is the chemical reaction. What is the chemical reaction that is happening in that particular cell? And what is the redox? How many electrons are flowing? Who is gaining? Who is losing? Why? And so on and so forth. So basically, these are some of the aspects that we are going to cover in this electrochemistry. So we'll meet next time, and please make sure that you join quickly so that you're not disadvantaged. And I believe someone was handy when it comes to coding, so that you can share with colleagues that were able to make it to this meeting. I hope we'll do justice to everyone so that they're not disadvantaged. Okay, so from here, we'll meet next time. Have a good